So I'm going to go over all the questions on the review for test 2. If you haven't had a chance to look over this on your own, I want you to stop the video and take some time and actually work through the review, and then you can compare your answers to what I show on the video. That way you're actually actively trying to do it on your own. But also sometimes we can get, fooled into thinking we understand something because we watch someone else do it, okay? And it would be better for you for preparation for the test if you could do it without guidance. Okay. All right, so let's look at number 1. Use a table to answer the following question. So in a certain college class, the ratio of men to women is 4 to 3. So we have 4 men for every 3 women. Remember back when we talked about ratio, this is what we would call a part-to-part comparison. Okay, it's not a part-to-whole comparison, so it's not actually really a true fraction. Remember we talked about that. So when you use a table, the table is just honestly organizational. So you're going to line up the ratio of men to women, which was 4 to 3. And then notice it says if there are 24 women in the class, then how many students are there in the class? Okay. So then you look for the pattern. Okay, because we're trying to learn how to teach this, we would line 24 up here, right, since it describes the number of women. And then we would say, hey, we multiplied by 8 here. So in order to make this complete, I need to multiply by 8 there. And then I get an answer of 32. Okay. Notice I always need to read the problem, right, because this asked me for the total number of students. So in the end, I don't just need to say 32, that's how many men there are, right? It would be 32 plus 24 for a total of 56. Okay, so we had some other problems. You want to go back and look at the old lecture videos or go back and look at your homework, but you had plenty of examples where we used a table. This is just one of those. Okay. Number 2, I asked you to use a proportion and then round to the nearest 100th. So we have 23 touchdowns scored in the last 17 quarters. So based on this ratio, it says how many touchdowns to the nearest 100th would he throw in a normal 4-quarter game? So if I have 4 quarters, the question is what would go here? Okay. And remember, when I'm doing a proportion, I can cross multiply. I can call my unknown x, right? And then I have 17x equals 23 times 4. Or I have 17x equals, if I use a calculator, 92. And then if I divide by 17, I get an approximate answer, right? If I asked you to round it to the nearest 100th, that's 2 decimal places. So it's basically 5.41 on average TDs per game. By the way, just kind of a side note, notice that I didn't assume that everyone knew that 4 quarters was in a game. Okay, so when you create problems for your students to do, if you pick different interest type problems, like if you pick a sports question, you can't assume that all of your students have the same sporting knowledge that you do. Okay, so you would want to make sure that you were clear that 4 quarters is actually how many exist in a game, so that they don't get tripped up on a football question when actually you really want them to know how to do the ratio. Okay. Number 3, you will have at least one problem where I ask you to use a personometer. And then you will have other problems where you may use a personometer if you wish. I personally like the personometer. Maybe you don't. So I'm just giving you a heads up. You'll at least have to do it on one, and then you'll have an option if you'd like it to do it on some others. Okay, so let's read through the problem. A mathematics test had questions totaling to a value of 106. So if it's the total, that's going to be the 100%. Okay. A student, or Wendy, scored 92 out of the 106 points available. What is her percent score? So 92 is going to be down here pretty close to 106, right? And so the question is, what goes in this box? So all this is organizational. It just tells you how to set up your proportion. So x over 100 equals 92 over 106. Okay, and then just make sure you show your cross multiplication. So you would have 106x equals 92 times 100, or 106x equals 9,200. And then last but not least, we'll divide by 106. Remember I said originally, I don't want you to multiply or cross multiply and divide all in one step. I want you to keep them separate. So this comes out to be 86.79%. Okay. Notice it's less than an A because it's not out of 100 points, right? She got 92 out of 106, which means basically that each question was worth a little bit less. Or each point was worth a little bit less. For number 4, I just want you to look at a lot of the in-class worksheets that I had you print out. So I'm going to remind you of a few of those, but you need to make sure that you know how to. There was a worksheet with you had to pick whether it was a ratio, a fraction, or both. Okay, that's one I can think of. There was one with blue and green cubes. And it was to do with proportions. Okay, so I'm just going to say etc. So those handouts that I refer to in the lecture notes, you'll want to be familiar with those. You might see questions like those on the test. All right, so the next little group, you're allowed to use any teaching style or any style you want, but it needs to be something where you're very explanatory. You're explaining every little step. So suppose a flower bouquet has 13 roses in it and 9 carnations. If you take away 4 roses and 4 carnations from the bouquet, does the ratio of roses to carnations increase, decrease, or stay the same? So when you're not sure how to tackle a problem, just start listing the information you know. Okay, you know that in the beginning we have 13 roses for every 9 carnations. Notice this is a part-to-part comparison. If you were to divide them, you are going to get 1.4 with a bar over it. So let's talk about what that means. That means there are 1.4 with a bar over it roses for every carnation. That's what it means. It means the ratio. So in other words, really you're thinking of it like 1.4 to 1. Okay, even though sometimes we don't write the 1. And then once we make the change, notice if you read the problem, we're reducing the number of roses by 4. And we're also reducing the number of carnations by 4. So in the end, we get 9 roses for every 5 carnations. And this works out to be a ratio of 1.8 over 1. So notice the meaning of this. This means there are 1.8 carnations. Sorry, not carnations, roses. Since roses is on top for every carnation. Okay, so notice the ratio actually increased. The point of this is really to show that the ratio changed, okay? And this is a common student mistake that we talked about in the lecture video when we discussed ratios, but this shows that you are not allowed to subtract the same number on top and bottom because you won't maintain the same ratio. Okay, remember you are allowed to multiply on the top or the bottom or even divide the same number on the top and the bottom, but you are not allowed to add or subtract. And the fact that the ratio changed at all demonstrates that. Okay, it just so happens that it went up. Okay, so number 6. I do want you to remember what the lecture video said about problems like number 6, so let's read through it. Judy received an 8% salary reduction. So I do want you to remember that salary reduction means subtract from 100. In other words, instead of worrying about her 8% reduction, we're going to focus on the fact that she kept 92% of her salary. So sure, she lost 8%, but she kept 92% of it. And then you can either set up a equation here, okay, or this is the part where it's optional since I didn't state you had to use a percentometer, but you need something to organize your data. So you need to explain yourself if you're not going to use a percentometer, but unless I state that you must, you don't have to. So here we're comparing percentage to salary, okay. Notice we always put 100 here, right? We don't know what her original salary was, but we know that 92% of her salary was $41,731. So this is actually what we're solving for. So if we have 92 over 100 equals 41,731 over x, and then if we cross multiply, we're going to get 92x. When you multiply something times 100, you can just tack on 2 zeros. And then we'll divide both sides by 92. And so if you use your calculator for that, you're going to get about $45,359.78. Okay, if it's money, make sure that you round it to the nearest penny. Okay, we don't round it to the nearest dollar, so some people care about their pennies, right? So we want to make sure with money that we're pretty accurate. Notice it should make sense to you that it's more, right? She was making $41,731 after the salary reduction, right? Which means before that she should have been making a little bit more. Okay, notice it's not a ton more, right? It's not like double or something because it was only, only an 8% drop. So if you don't want to use a percentometer, here's the kind of work that I would expect to see. Okay, you would call X her original salary, and you would state this so that you're showing all your steps so that someone who doesn't know what we're doing can follow along. And you would still need to talk about that we are keeping, or she is keeping, 92% of her salary. So notice I have 0.92, and that equals the 41,731. Notice that there's maybe a little less to show here, but I think that when you're trying to think about teaching younger students, I think this is not quite as clear. Okay, that's one of the reasons why I really like the percentometer. It organizes our data, and I think helps us set up the proper ratio without too much trouble, and it'll help our students that way too. But it's optional. You don't have to do a percentometer on this, but you would have to have either. Okay, either explain it this way or explain it that way. Okay, number 7. We're trying to figure out who is right. So let's start with what Susan says. So Susan says that she has 20% less than Sharon. Okay, so notice we're taking 20% less. So let's write this as kind of a mathematical sentence. That means Susan is saying that she, Susan, is 80% of Sharon. Okay, how did I get 80%? Well, if it's 20% less than, then I subtract 20% from 100%. So let's see if this works. We already know that Susan has $20. So the question is that 80% of what Sharon has, which is $25, okay? And I'm going to put a big fat question mark here because I'm not sure this is right. I'm trying to evaluate who is right, okay? And notice, though, if you check this with your calculator, that you do get 20 on both sides, okay? In other words, what does this tell you? This tells you that Susan is correct. Okay, so it would be hasty for you to stop right there. You should always maybe check the other one. Okay, remember in math, sometimes we want to answer the best answer, not just necessarily the first one that comes up that seems right to us. We want to give the best answer. So this is what Sharon says. She says that she has 25% more than Susan. Okay, so remember, we handle more than problems by adding the percentage to 100, right? So if I had to write a mathematical sentence, Sharon's saying that her money, okay, so Sharon is 125% of Susan. Okay, how did I get 125%? Because I added 25% to 100%, right? So let's see if that works. So Sharon, we already know, has $25. If we move the decimal place twice, we get 1.25. So the question is this correct? Okay, notice I put a question mark because I'm not sure. And notice if you punch this in the calculator, it is correct. So you would have been hasty to stop with the first one because notice that Sharon is also correct. So make sure you follow a problem all the way through because the correct best answer is that they're actually both correct. Which seems weird, right, since they're saying different percentages, but the difference is that they're saying percentages of different values. Okay, one of them is saying a percentage of the larger number, and the other one's saying a percentage of the smaller number. Okay, so number 8 is when we started talking about sets and percentages. Okay, so you need to go back and look at that handout that I gave. It's got lots of examples. It's got pictures of stars and trees and all kinds of things. Okay, you need to go back and maybe look at some of those because there's only one example here. So I said if there are 8 chips in a set, so by the way, if we say a set, 8 in a set means that it stands for the 100%. Okay, if you're not sure how to read that. So I'm going to draw 8 items, and I'm going to make sure and say that that's 100%. But notice I want to talk about 225%, so I'm going to skip a little space. So let's see about how I could break up 225. Okay, I could probably talk about 100% plus another 100% and then plus 25%. Right? So the 100% are fairly simple, right? We just need full sets, but we will also need to break the sets up into 25% sections. So you need to come up here and section these off into 25% pieces. Okay? Notice this piece is 25%. So is this. So is this. So is this. You don't count up, like don't write 50% here. Each of those sets that I boxed in, each of them is 25%. So now, since I showed that, I can show that we have 1, 2, 3, 4, 5, 6, 7, 8, right? Here's a full set. And then I'll add a second full set. So each of these representing 100, right? And then I also need another little tiny subset, right, of 25%. It's okay that I don't really label this here as far as going under it goes because I already did up top, but I would want to label it somewhere. Okay, so notice that the grand total is 225%. Or 18 chips. Okay. Make sure that when you're studying this that you can do things like 50%, 25%, even 33 1/3%. Remember all of those what we called benchmark percentages, you need to make sure that you know how to do those. Okay, so this is just one example. The review is just kind of a launching pad for you. You need to go back and look at other problems that we did in class if you really want to make sure you're completely prepared for every possibility on the test. All right, number 9, explain in your own words what 36% means. Okay, so we discussed this in one of the videos as well when I introduced percent. Percent literally means per 100. So when you see 36%, it quite literally the name means 36 out of 100, okay, or 36 per 100, if you wanted to say it like that. By the way, this is why we move the decimal place twice when we change things from a percent to a fraction. Okay, you know that rule, we always use that rule, right? But the reason we do is because we're really dividing the number by 100. Okay, so it's why we move the decimal place twice when changing from percent to decimal or vice versa. Okay, and it's because the hundredths place, if you understand place value, is literally 2 decimal places. That's why. So just kind of a side note. That's really extra for the problem that I asked, but I'm just saying, okay, that is why we move the decimal place twice. Okay, so before we get to number 10, I just want to remind you of the benchmark percentages. I kind of already verbally went through some of those. So the main ones are 10%. By the way, how you do that mentally is you move the decimal place once. Okay, so that's like how I tip in restaurants. I figure 10% and then I double that because I like to tip 20% if I get decent service. And a little less if I don't, or a little more if I get awesome service. Okay, but move 10% is really easy, and then you can go off of that and figure 20 or 30% or whatever. 50% is another one. 50% means 1/2. 25% means 1/4. Remember, benchmark percentages, any type of benchmark is just something that we use to compare other values to. Okay, 100% means 1 whole. And then lastly, make sure you know this one and the one that's close to it. 33 1/3% means 1 out of 3. Okay, it means that because if you do 33 1/3 over 100, 33 1/3 literally takes up 1/3 of the 100. Okay, so by default, that means that 2/3 would be double. So if you double 33, you get 66. If you double 1/3, you get 2/3. So 66 2/3% means 2/3. Okay, so really if you know this one, I think you can get that one by doubling it. All right, so for 10 and 11, let's do the mental math. In other words, I should not have any indication that you used a calculator. I should only have the things that I feel like you can do mentally, or that a student could do mentally, or that I can do mentally. Okay, so the first thing is maybe we should think of 133% and a third, 133 1/3%. Maybe we should think of that as 100% plus 33 1/3%. Okay, so first I would find 100% of 90. But 100% of a number is just itself, right? So 100% of 90 is 90. And then 33 1/3% means 1/3. So 33 1/3% of 90, think of 1/3 of 90 is 30, right? So in the end, I'm going to put a star by this. You would need this statement. 133 1/3% of 90 would be 90 plus 30, or 120. In other words, we combine the 100% of 90 plus the 33 1/3% of 90, and we get the 120, or the 133 1/3% of 90. So same kind of thing on number 11. use mental techniques to find 325% of 60. So 325% of 60. So first, maybe we should think of this in this way. 325% is really just 3 wholes, right? Or 3 100%, and then plus an extra 25%. So notice how I explain everything and leave nothing to the imagination. First, 100% of 60. By the way, you should always say a percentage of a number, not just the percentage by itself when you get to your explanation. 100% of 60 is 60. So 300% of 60 should be 3 times that. Okay, and 3 times that is 180. And then 25% of 60 means 1/4, right? So 25% of 60, a fourth of 60 would be 15. And notice in the end we still say the full, right? So 325% of 60 would be the 180 plus the 15 for a total of 195. Okay. So you could have technically done like 300% and then a 10% doubled plus another 5%, but that's kind of the longer way. So if you can use it using the benchmarks, or do it using the benchmarks that I listed above number 10, then you should be good to go. Okay, number 12, you just need to review pie charts, bar graphs, line graphs, histograms, frequency distributions, all of those things we did in that data representation section. You had a homework assignment about that. We took some notes on that in the video lecture. You just need to go back and look at all of that. You also need to know kind of maybe when it's appropriate to use which of them. Okay, when does it make more sense to use, for instance, a pie chart compared to a bar graph, and vice versa. Okay, so not really anything to show for number 12, but you definitely need to go back and look. Okay, so before I get to the probability questions, I just want to go over kind of some probability basics. The first thing is just the straight up probability formula. The probability of an event A is the number of occurrences of A over the total possibilities. Some other things that you might want to keep in mind, you'll need to make sure that you give me reduced fractions. And make sure you can change from a fraction to both a decimal if asked and a percentage. Okay, spoiler alert, you divide the fraction to get the decimal, and then you move the decimal twice to get the percentage. But make sure you could do it in all forms. I might ask you for different forms. I might say, change this fraction to a decimal rounded to 2 decimal places. Or I might say, give me a percentage rounded to 1 decimal place. Like, you need to make sure you read the directions there. And then just make sure you know basic things like coin toss, drawing marbles out of a bag, any type of spinner. I gave you some examples on the video of some different looks to the spinner. Okay, you might see a die roll. Remember, a die doesn't have to be 6-sided. Okay, it can be, you know, as many sides as we want. Definitely make sure you familiarize yourself with a deck of cards. I'm going to underline that one. Okay, so some of the things I gave you kind of the rundown on about a deck of cards, make sure you know those things. Okay, so let's look through number 13 and 14. You know, these probability questions don't really take all that much time, but just make sure that you can explain what you're getting to. So I'm going to number these or letter these A through whatever, but I didn't necessarily do that on the review, but I think you can figure it out. Okay, so let's do the first one. The probability of getting a 4 when you roll a fair 6-sided dice or die. Make sure you know how to write this, right? This means the probability of 4. Okay, so notice this would be 1 out of 6. If I asked you to tell me why, here is why, right? This is the number of desired occurrences, right? In other words, this is the opportunity for me to get the 4 that I want, okay? And then notice what's on the bottom is the total number of options. So if this weren't a 6-sided die, you would need to, you know, practice that. So this would be the reduced fraction. But remember, I might also ask you to give it to me in a decimal form. This is actually 1.6 with a bar over it. If I asked for it in decimal form, and let's just say I asked for 2 decimal places, or sorry, in percentage form, then you would need to be able to do that as well. Okay. Notice the last one is a 7, because if you keep repeating 6s over and over, then that last 6 will bump up this 6 to a 7. Okay, the probability of getting an even number when you roll a fair 10-sided die. Okay, so if you have to, then you might even list out the numbers if you think it's helpful. Okay, so the probability of an even number on a 10-sided die. Okay, so that's significant, right? So think about all the even numbers, right? And we're going to assume that the die is listed 1 through 10, right? So we have how many even numbers in between 1 and 10, okay? Notice we have 5 of them, right, out of 10 total choices. So here's my explanation. There are 5 choices that are even, right? And there are 10 total choices. So that's my explanation, but notice if I asked you to reduce it, then you would. Okay, so 1/2 would be 0.5, would be 50%. So just make sure you reduce it if it can reduce. The third one on number 16, or 13, sorry, the probability of getting a jack. So the probability of jack, or you could say J for jack. Okay, so there's 2 ways to think of this. Remember we talked about this when we looked at it the first time. You can either compare how many jacks there are to how many cards in the deck, right? So this represents the number of jacks, and this represents the number of cards. But another way to think of that is 1 out of 13, which is, by the way, what 4 over 52 reduces to. Okay? And if you do that, you're thinking of there is one option that is a jack out of 13 choices. Right? Remember we talked about that. If you go ace all the way to 10, that's 10 choices, right? Plus jack, queen, king, that's 3 more. So for a total of 13 choices. At any rate, this is the answer that I want. Whether you start off here or whether you go straight here, I'll want the reduced version. So if I asked for a decimal, you might have this, which is about 7.69%. I usually request 2 decimal places to the percentage, which means that I'll need to write 4 decimal places for the decimal so that when I move it twice, I still have 2 in the percentage form. Okay, so the fourth one, the probability of getting a spade when you pull out a single card from a deck of cards. So 2 ways to look at this. You can either say there are 13 spades, right? Because there is an ace through king of spades, okay? So notice this compares the number of spades to the number of cards. Or you could talk about what this reduces to, which is 1 out of 4, okay? Notice we have one option here, right, out of 4 total suits, because it could be a spade, it could be a heart, a diamond, or a club. But again, reduced fractions are what I'm going to want. So this would be 0.25 or 25%. Notice anytime I round, I'm using the approximately equal to symbol, and then anytime I don't round, I'm just using a plain old equals. All right, so let's look at the last one, and then we'll look at some compound probabilities. So the probability of red. So one of 2 ways to look at it. You can talk about that there are 26 cards in the deck that are red. Okay. Another way, you can say 13 diamonds and then 13 hearts, but they're all red, right? So this represents the number of reds. This again represents the number of cards. Or notice this reduces to 1 out of 2. Okay, and that is because we have one option that fits our requirement, right? That is red, in other words, out of 2 color choices. But at any rate, I'll circle this one, and we want 0.5 or 50%. Something that maybe I didn't mention, make sure you know what a face card is. We talked about this in the video before. A face card is literally a card with a face. So it's a card with a person on it. So that would be all the jacks, all the queens, all the kings. Aces are not included in the face cards, okay? In a lot of games, an ace is a good card to have, but it is not a face card. All right, so for 14, the first one just says various and or problems. So for part A, just make sure that you know these formulas. The probability of A and B is the probability of A times the probability of B, as long as A and B are independent. In other words, as long as they don't have anything to do with each other. And if they do have something to do with each other, you have to make an adjustment. Okay, we talk about that when we talk about with replacement versus not. So we'll get to some of those examples here in a bit. But the probability of A or B is the probability of the first plus the second minus the probability of A and B. Okay, remember this avoids counting a single item twice. If there's an item that shows up in both categories, you don't want to count it twice, so you take off the double count basically. Okay, so let's look at the second one. The probability of having your first and second child be boys. Okay, so it's like the probability of 2 boys. Each of them are independent, right? Each of them have a probability of 1/2, and then since we want those things both to happen, we would multiply this. So this would be 1/4 or 0.25 or 25%. Okay, the third one says the probability of flipping a coin and getting at least 1 heads. I bolded that for a reason. So I'm going to say on 4 flips of a coin. At least 1 is difficult to find directly because at least 1 means 1 or 2 or 3 or 4. Okay, the only thing that it does not cover is 1 minus the probability of no heads. So we're going to go kind of the backwards way on this. We're going to figure out the opposite, and then we're just going to take it away from 100%. It's a lot easier to do that way. So let's look at that. The probability of no heads implies that they're all going to be tails, right? So if the first one's a tail, the second one's tails, third is tails, and fourth is also tails. And you have to multiply them all, right? Because 4 events have to happen. So this is like 1 minus 1/16, which is just 15/16. Okay, and use your calculator, but 15/16 is going to be 0.9375 or 93.75%. All right, part D, the probability of getting a red card followed by a 4 if you draw 2 cards from a deck with replacement. Okay, so let's talk about the 2 events that have to happen, right? We want the probability of a red first and then a 4. Okay, so it is an and problem. We want both things to happen. Okay, so notice this time I said with replacement, right? So let's figure that out. The probability of a red first would be 1 out of 2, or you could say 26 out of 52. Look back up at 13E if you're curious about where I got that. And then times the probability that we get a 4, okay? So you can either say 4 out of 52 or use the reduced version. Notice this is the first event that I want to happen, right? And this is the second event. Okay, notice it's significant that this problem said with replacement. Okay, with replacement means we put the first card back before we draw the second. Or if we're doing marbles or whatever, it means we put the first item back. So this is 1 out of 26, which is around 0.0385 or about 3.85%. So notice this is a completely different question when I say, I'm going to do this to say it's the same, right? But without replacement. So notice that doesn't change the first event. The first event is still going to be 1 out of 2 or 26 out of 52, however you want to write it. Okay, but it does change the probability of the second item. Okay. Okay, so sorry, I was thinking about that for a minute. Trying to make sure I didn't make the problem unnecessarily difficult. All right, so this time we have 1 card missing. Okay, so I do actually think I need to change this question. So I'm going to upload the correct one. So I want to ask a different question. The reason is just what I said. You have to be really careful with probability that you don't ask a more difficult question than you mean to. The problem is the red card that I choose could actually be a 4 or it could not be a 4. And it's not my intention to make that, you know, this complicated. That's not what this is supposed to be. So I want to change that problem to the probability of, let's say the probability of a 2 followed by a 3 but without replacement. The reason that's an important change is because notice it can't be both a 2 and a 3. That was the confusion about that 5th one. It could have been both a 4 and a red card. Okay, so I don't really want to get into that. The probability for that is actually quite difficult, and that's not my intention. But the key here is, since I'm going to change the problem, okay, so I'll go back and change that here in a little bit, so most of you probably won't even see the problem written like that, Okay, but go ahead and change it if you have already printed it out. So the probability of 2, okay, so let's think about that. The probability of 2 would be 1 out of 13 or 4 out of 52. But the difference here is when you get to the second one, right? This is the first card drawn. When you get to the second card drawn, something has happened, right? We did not replace one of the cards. So we can't say 1 out of 13 again because we don't have 52 cards, okay? And the only reason we can say 1 out of 13 for the first one is because 4 out of 52 reduces to 1 out of 13, okay? So notice we only have 51 cards left because we took one of the cards away. But we still have 4 3s left. So I know that's a little strange, right? But we end up getting 4 over 663. And if you divide that out, you're going to get 0.0060 or about 0.60%. So the caution when creating probability questions where you're trying to be straightforward is the problem comes when you have a dual event or a compound event where the 2 events can overlap each other. And that was the problem with my original problem that I chose. Okay, the card could have been both a red and a 4, so that makes it a little challenging. All right, so and then the last one, what's the probability of getting a red card followed? So a red card or a 4 if you draw 1 card from the deck. Okay, so this is the only one we've had so far that was really or. So the probability of red or 4. Okay, so the or is significant. So remember the formula for that. It's going to be the probability of red plus the probability of 4, but then we need to subtract off the chance that it is both. Okay, notice it can be both a red and a 4. Okay, so that is an issue here, but it's an issue we can deal with on this one. So we can talk about red being 1 out of 2, okay, or you can just list it as 26 out of 52, and I'll talk about why I might do that on this one. Okay. So there are 26 reds out of 52. Notice we're only doing 1 draw, right? So we don't have to worry about replacement or not. There are 4 4s, right, out of 52 cards. And then you need to think about how many red 4s are there. How many cards are there that are both red and 4 at the same time? There are 2. Notice why I wanted to have the unreduced fractions here. Notice I have a common denominator. So now I have 30 take away 2, which is 28 over 52. But make sure you reduce that. So 4 goes into both of those, right? So if I asked for a reduced fraction, you would need to give me 7 over 13. And that's about 0.5385 or about 53.85%. Okay. Okay, something else that I can think of, just make sure you know how to list things like the sample space. Okay, remember the sample space is where we used curly brackets and or curly brace, and we just list all the possibilities. Okay, so make sure you know how to do that. It says at the end, be familiar with the difference between theoretical probability, okay, and experimental or empirical probability. So theoretical is what should happen. So go back and look at the original video. I gave a better definition of that, but it's what should happen based on theory. But empirical, these two terms are interchangeable. Empirical and experimental are the same. And experimental is what does happen based on results. That's why it's often called experimental probability. Okay, and it turns out these two things will be most alike or closest when the number of trials is large. Okay, and that is called the law of large numbers. So if you only do an experiment twice, we talked about this with a coin toss in the earlier video, if you only tossed a coin twice, you would not get as accurate results as if you tossed a coin 1,000 times or 100 times or even 10 times. Okay, twice would not be sufficient. Alright, so that should give you kind of a starting point when you're trying to figure out what you should review, and then you're kind of on your own to kind of make sure that you know the things in the lecture video, that you've paid attention to the homework and the handouts. Everything since test 1 is kind of up for grabs on this test.